Welcome to lesson 3 of the Math 3 module. Today we're going to talk about trees, spanning trees, and as last we're going to look at Dijkstra's shortest path algorithm. And Dijkstra being a very famous mathematician, and he worked at the Technical University here in Eindhoven. So the subjects we discuss are can be found in the book 8.8, but most important one is in the reader, chapter 3, where the Dijkstra algorithm is discussed. So let's start with a tree, and in fact we already looked at a tree when we had the breadth-first and the depth-first algorithms introduced. A tree is just a graph which has no cycles but is connected. So, for example, this first one, that is not a tree. It doesn't have cycles, so that one is okay, but it's not connected. Here, the first three elements are not connected to the other nodes. So this is not a tree. Second one, it is connected, but it also has a cycle. We can go from this point and then just walk around and go back to that same point. So that's a cycle, so not a tree. And then this one, that's a tree. So it's connected. Every node has a connection to the complete graph, but also if we go someplace, we can never continue and find our origin again. So we can't find a path from the beginning and end in that beginning again. So that's a tree. If we look at this graph, then a subgraph T is a subgraph of this connected graph G, which is a spanning tree. So it is part of this one, but it also represents a tree. So if we look at some examples, so for instance this one, so these nodes are all part of the original graph, that is correct. And unfortunately, we don't have these vertices here, and the spanning tree should include all possible vertices of G. So it is a tree, but not a spanning tree of G. The next example, this is really a tree, so we have a nice tree, we can start, we don't have cycles, everything is connected, but again, unfortunately, this is not a subgraph because this edge here is not part of the original graph. So no, not a tree because it's not a spanning tree because it's not a subgraph. Okay, and the last example is a perfect one. All the vertices are there, all the nodes are there, and all the edges are part of the original collection, and we have no cycles. This is a spanning tree of the graph G. Okay, if we have a graph G, then we can make spanning trees in different ways. For instance, we can make this one. So just we have A, B, C, that's this part, and we have C, F, and this one, and then we just drop these edges, so there are no cycles. Perfect spanning tree. But this example is also a perfect spanning tree. So as long as all the vertices are connected, no cycles, and every edge is part of the original graph. Perfect spanning trees. How to make a spanning tree? Well, we can use the depth-first and the breadth-first algorithms we discussed in the previous lesson. Let's start by using the depth-first algorithm. We have to start somewhere, and they suggest let's start at index 1. And then it's a depth first, so that means we go as deep as possible. So we don't go back until we have to go back. And when we have a choice, they suggest choose the one with the smallest number. Okay, so we start at 1. Then we go to the smallest number, 2. Okay, 2. And we go deep. So we continue to the smallest number, 3. And from 3 we can go to 6. And that's our only option, 6. From 6 we can have 3 options. We go to the smallest number, 5. Then from 5 we can go to 7 or to 8, but 7 is the smallest. And then from 7 we go to 4. Okay, and it's good we can't get any further because I drew at the end of my paper. Because now we have to go backtrack, they call it. So we have to go back until the first moment we could have made a different choice. So that would be at option 5. So at 5 we could also have gone to 8. Okay, good. We go to 8. And from 8, yeah, we can only go to 9 because we already have done 6. And that's it. So now we've made a nice spanning tree with the depth first algorithm. And that is the spanning tree. And you can just leave it as it is and just leave the original shape, but you could also represent it in the way we normally see a tree. So with nodes and then with extensions, like a Christmas tree. We can also use the breadth first method to find the spanning tree, and in this case we take neighbors in alphabetical order and we start with A. Okay, let's immediately make a nice tree out of it. So A. And then from A we can have B, we can have E, and we can have D. And they said we have to do it in alphabetical order. So we'll take B, then D, and then E. And let's take them out so we know we've been there. Okay, then on our next level, because it's breadth first, from B we can go to C and to F. So C and F, and let's take them out. From D we can only go to G, that's the only one. And from E we can go to H. So that's another level completed. And then there's only one node left, so let's see. Is it connected to C? No. To F? Yes. So this node should be here, because we have to start from the left again. And then we have made a nice spanning tree with the breadth first algorithm. If we compare the two spanning trees, then you will find that, of course, with the depth first search, you will normally get very lengthy trees, and with the breadth first search, they will be more compact. And it's not a real difference. Sometimes you also have to solve a problem and make a spanning tree when you have a weighted graph. So then the edge itself has some cost, some weight inside, and you have to take that into account for your spanning tree. And so, for instance, we have 6 computers connected to a network, and an edge indicates that we can connect those two vertices, those two computers. But the weight tells us something of the price to do so. And then a question is, what is the cheapest way to make a connected network for these computers? And in fact, if you talk about the mathematical, what they ask you to find is the minimum spanning tree. So what is the spanning tree we can make with the lowest cost to get from one computer to the other? And so to summarize, a minimum spanning tree is a spanning tree of which the sum of the weights is as small as possible, so as less expensive as possible. And an algorithm we'd like to discuss with you is the one thought of by Joseph Kruskal. And the algorithm of Kruskal is quite straightforward. What he thought of is, we'll just order the edges with the lowest weight first, and we'll put them in a row. So we have 7, 7, 9, 9, 10, 16, 24, 38, 70. And then we'll just choose edges one by one, with giving priority to the ones up front of the row with the lowest weight. And if we have a cycle, we don't allow that edge to enter the minimum spanning tree. So if we do it like that, at the end we will have a spanning tree with minimal cost. So let's just start. So we take this one, 7, and then we have another 7. That's good. So these two are done. Then we can pick a 9. Let's take this one. Okay. And then we have another 9, but you see we can't take the other 9 because this would create a circle. So this is out. Then we look at the 10. Well, the 10 is standalone so far, so that's perfect. We look at the 16. Okay, it's also a possibility. No problem. And in fact, we're already done now. We don't have to look any further because we have all vertices connected and no cycles. So this is a result, as a result, is a minimal spanning tree. And the cost of this connection is now 7 plus 7 plus 9 plus 10 plus 16, and that would be 49. And this is the minimal cost we can spend to make this computer network. Unfortunately, the algorithm of Kruskal, it looks very elegant if we draw it, but if you have to implement it in a computer, it's quite difficult, because you don't keep the thing connected. You have standalones, and every time you add an edge, you have to check, will it make somewhere a cycle? So that's quite difficult. And then Mr. Prim thought of another way to solve this puzzle. And Mr. Prim said, okay, we'll just don't randomly, almost randomly, we just don't take all edges when they are the lowest in price, but we'll keep it a tree. So it's not allowed in Prim's algorithm to have such a detached element like this edge 10, which we saw in the previous algorithm. So we keep the tree a tree. So again, we start at a low cost edge, so that would be this one, 7, and then we keep this tree a tree, so that means I can only expand with a connection to one of the vertices we already have, and then we choose the lowest possibility. So in this case that would be this 7. So now we have a tree with 2 elements, computer and 7 with 2 edges. Okay, then we can expand this tree, but it has to be connected with one vertex outside of this tree. So that could be this 9 or that 9. Now, let's take this 9 again. And again, we can extend. This 9 is out, because now we see this 9 will go to a vertex, to a computer we already used, so that's not allowed. And in the previous algorithm we would now have chosen 10. But in Prim's algorithm that's not allowed, because this edge with the very 10 is not connected to the original tree. So we have to choose now with something which is connected, so that's either 38 or 16 or 24 or 17. Okay, 16 is the lowest one, so we choose 16. And then again we find an edge with the smallest weight connected to the original tree, and that's this one. So in fact we should again have a very efficient spanning tree with a minimum weight, but the way we discovered it was a little bit different, and that's Prim's algorithm. Another puzzle which needs to be solved quite often is to find the shortest path in a weighted graph. And it's not a complete tree, but you want to find a route from one vertex to another vertex. A lot of algorithms are available. If you're interested, you could check out Warsaw or pruning algorithm. But what we are going to discuss in this course is Dijkstra's algorithm. Okay, let's start with a very practical example. You are in Eindhoven. okay, and you want to go out in Eindhoven and you're at this cafe, de buurvrouw, in nice Dutch. And then you hear from students that in another cafe there will be a happy hour, so you want to rush there. And you have several routes to get there, to this happy hour, but these routes take time. So what we'd like to find is the fastest route to get from de buurvrouw to Café de Stunt, the fastest route. And for this problem, Dijkstra found an algorithm. Dijkstra's idea was to make a spanning tree, but not a complete one. It didn't have to include all possible nodes, but only still considered the best expansion to get from one end to the other. And how he did this is he thought, okay, every node, every cafe or every point or every computer is given an ordered pair with two meanings. The first one is the length or the time or whatever is your waiting issue to get there so far, and where do I come from. And so, for instance, if I have A and it cost me 4 kilometers to go to B, then this point B here would have the length 4 and it comes from A. And if I would continue from B and go to C, and let's say this cost me 11, then C would have 11 coming from B. So this 11, this grade, would be the total length so far from your origin to where you are now, and the source, is in fact the last node you visited. So where did I come from? Okay, to calculate this, we initialize the starting vertex with 0. We didn't go anywhere yet, and we didn't come from nowhere. We are here, 0, 0. And all the other vertices are initialized with infinite, because every time I come there, then the route so far will be shorter than this infinite, and I don't have a source yet, so it's still empty. Okay, it's a little bit vague maybe, but let's show how this works in practice, and then you'll get the hang of it. We have this cafe, and this cafe A will be initialized with 0, 0, because that's the starting point. All the other vertices, so B, E, H, etc., will be initialized with infinite. I wasn't there yet, and I don't know with what node from who I will come here. And then we start iterating. And with every iteration, we keep track of the length of the path so far, and we'll continue always from the shortest length so far. So we don't expand with every possibility, but always take the cheapest choice how to expand. Okay, so we are starting in A, and then we have 3 options. We can go to B, to C, or to D. If we go to B, that'll cost us 14. So we change B into 14, that's the length so far, and we come from A. But C is much more cheap. It only costs us 2 to get to C. And if we want to go to D, it'll cost us 4. So now we have a first iteration, and then the second iteration, we don't choose every possibility, but we take the one with the lowest cost so far, and that's definitely C. So from C we take all possible options. So we can go to F, so this F would take 2 plus 5 is 7, and we get from C. And we could go to G, so G would be initialized, filled now with 2 plus 6 is 8, coming from C. Okay, and that's the only one we can have. So the total, the cheapest one so far is, if we look at it, we have 7, we have 8, we have 4, and we have 14. So definitely that is D. So let's look where we get from D. So from D we can go to G, and look, that's nice. 4 plus 2 is 6. So apparently if we go to G via C, that's more expensive. So we replace this one and we change it with 6 coming from D. Okay, we were at D and this was the only root, so that's it. Next iteration. Find the cheapest one. And the cheapest one now is this 6, 6D. And from this 6D, so from G, we can go to H, and that is our destination already, costing 7 to get there. Okay, now we're done, because we arrived at the spot. And we also have a 7 here, 7C, so that's just as expensive. But to get from 7 to H, it'll cost us more. So definitely this route is the cheapest one. So we'll just trace it back. This one, that one. So the route is A, D, G, H. And it'll cost us a total of 7. Great. So this is Dijkstra's algorithm. Let's practice. So we've given a graph, and let's try to find the shortest path from U, so this one, this node, to V, and then using the algorithm of Dijkstra. And to help you do so, it's easy if we make a table. And on the exam, if we ask you this question, then we will give you a corresponding table. So we start with initializing. So U is 0, 0, and all the others are infinite empty. So in the first iteration, we start with all possibilities getting out of U. So we can go to F with 3. So that's 3U. We can go to G with 4. We can go to D with 5. We go to E with 9. And we can go to B with 8. The other nodes we can't reach from U. And then this node is done. So we don't need to worry about these anymore. Then we look at the possibilities and we seek the smallest one, and that's F. So let's already put a V there. So we are checking this one now, and then we don't have to look at it any further. So from F we can go to V already. So that is 3 plus 10, that's 13. Okay, so we already found a path. That's great, huh? So we go and have an exit possibility already. So from F we can also go to C with the help of the length 2. So that's 5. And from F we can go to D, 12. So that would be 3 plus 12 is 15. Oh, I don't need to do that, huh? Because we already have a 5 in there. So we don't replace it. Then from F we can also go to G. But there's already 4 in there, so we don't do this one either. And we can go from F to U. Well, we don't need to consider that one, that's out. And we only have, so V, yeah, we're done, great. So that's F, done. What is the smallest so far? So we have a 4 in G, so that's the smallest. In the next iteration we're going to look at this departure. So from G we can go to F, but we don't have to look because that's already done. We can go to D with 9, but that's too long. We don't do that. So this one is not filling. We can go to U, that's done. we don't do it. And that's it. So from G there are no extra possibilities. So what is the smallest now? So we have the choice 5U in D and 5F in C. So let's do D. Iteration 4. So iteration 4 from D. Where can we go? Oh, that's the one in the middle. So we can go everywhere. So let's go from left to right. So from D to V, that'll cost us 7 plus 5, it's 12. Great, that's a new path with a smaller length. From D to A costs us 8. Okay, that is one we didn't have yet, so 13. And D, of course, 13D. And then from D to B, that'll cost us 2, plus the 5 we already have, it's a shorter one. And to C, it'll cost us 5, and it was already 5, so that would be 10, and we already have one with 5, so we don't do this one. And then to E, it'll cost us 1. That's a better one, because 5 plus 1 is 6, so we change this one. Great. Okay, so what is the smallest now? We have 7, 5, 6. So that's C with 5. So let's look at it. From C, we can go to V in 7, and 5 plus 7 is 12. We already had that one, we don't need to replace it. From C to A, that's not possible. Yeah, C only has D, F, and we already have done all those. So that's it. No rechanging. What is the next one to do? So we have 13, 7, 6. So E with 6. So from E with 6, we can go to B. And 6 plus 2 is 8. So no, we already have 7. So we don't do it. And from E to V is not possible. From E to A is not possible. And from E to C, yeah, that was already done. Done. The lower we get, the easier it becomes. And so we don't have any options anymore. So what is the smallest now? And then we only have 7 and 13 open. And 13 we can forget because our final part is already 12. So we can strike this one out immediately. And we only check out the last one, 7D, coming from B. So let's do that. We go from B, and the smallest part, the direct part, is with 4. And 7 plus 4 is 11. Great. 11. And coming from B. New path. Great. But we can also go to A with 2. And 7 plus, that's 9. That's a smaller one. And then can we reach E? Because that's the only one open here. From B to E, that cost me 2. And 6 plus 2, that's 8. That's too long. Okay, last one. So we have, the only opening is this 9. So from 9, can we go to V? I hope this is the last one. So from A, can we go to V? Yeah, and that'll cost us 1. Okay, great. That's a cheaper one. And we're done. So the cheapest route cost me 10. And if we backtrack, so it was V backtrack A, and from A backtrack B, and from B backtrack D, and from D backtrack to U. So the official path is U, D, B, A, V. So 5 plus 2 plus 2 plus 1. Great. And it's a good thing I don't have to do this on a daily basis, because I would really get completely shaky. Let's hope on the exam you get one with less iteration, with less possibilities. But of course, Dijkstra algorithm is not for a human to do. It's for someone to make a computer program, so the computer can do it. And he never gets shaky. So we will just do this nicely. Okay, this concludes our lesson. So I hope you enjoyed especially the Dijkstra algorithm, and just try it out for yourself. And please, if you do so, make sure you take your time and be very conscious and not make a mistake, because it's very prone for simple mistakes. Okay, you can make the exercises, and hopefully we see each other again in a Teams meeting, or you see me again in the next video.